Yes, your questions first. No.
Bir tane conducting sphere var. Etrafında da bir tane shell var. Ve bir
This is our conducting sphere with radius A. Then we have this shell B, V0 and V1.
Şimdi şurada şey gibi düşünsek hani A'dan büyük B'den küçükse ve B'den büyükse diye potansiyelleri soruyorum. Ortada bir charge varmış gibi düşünün. Çözebiliriz.
Almost. Almost. You see, in this problem, you can use separation of variables. That was what I had in mind to start with. But then there's a simpler solution also to this problem. Just say that the problem is spherically symmetric. These potentials will be created by surface charge densities on the surface, on the conductors. So let's say the outer sphere has a surface charge density sigma 1, and the inner sphere has a surface charge density sigma 0. At infinity, we will assume that the potential is 0. So V1. Well, when you consider V1 will be created by both sigma 1 and sigma 2, but both the charges will act as a point charge at the center. So the V1 is just 1 over 4 pi epsilon 0. Q1 plus Q0, let me call the Q0 and Q1 as the charges of the sphere and the shell, times 1 over A. And Q1 is nothing but 4 pi B squared sigma 1, and Q0 is 4 pi A squared sigma 0. So basically this, well, in fact, it's enough for us to find Q0 and Q1. So we have one relation between Q0 and Q1 from the condition that the outer shell is at the potential V1. Now we need to find the second condition. Now V0 will be one that will be the potential created by the inner charge. So that will be 1 over 4 pi epsilon 0, Q0 over A, plus V1. Because you see we have this outer shell, it creates an electric field outside. Inside there won't be an electric field due to this outer shell, so the potential inside will be constant. So the potential created by the outer shell inside the shell is always V1. So you can determine, from this equation you can determine Q0. From the first equation you can determine Q1, and you are done. So once you determine Q0 and Q1, you can just write down the potential anywhere you like. Let's do it using separation of variables now. So we have 3 regions in this problem. Region 1. Well, in fact, we don't need to worry about 3 regions. Let's say region 1, 2, and 3. Because if you look at region 1, we already know the boundary condition, the boundary value. Let's look at region 1. Okay, so in spherical coordinates, the most general solution of the Laplace's equation can always be written in this form, assuming the potential doesn't depend on the phi coordinate, which is definitely true in this case. There is no phi dependence. So A L R to the L plus B L over R to the L plus 1 times these Legendre polynomials. L from 0 to infinity. This is the general solution. Now let's look at the solution in region 1. First of all, in region 1, V is finite at R is equal to 0, because R is equal to 0 point is inside this region, in region 1. But if the potential is finite at R is equal to 0, all those BL terms should be 0. Because the BL terms are proportional to 1 over r, 1 over r squared, 1 over r cubed, all of which diverges at r is equal to 0. So the potential in region 1 should have this form. Now then we have the other condition that when r is equal to a, the potential is V0 for all values of theta. Okay, just a warning about the bad notation. ALs are the coefficients in the expression of the potential. A is the radius of the inner sphere. A to the power L is the power to the L of the radius. So we have this sum. Should be equal to V0, which we can also write as V0 times P0 cosine theta. Because P0 cosine theta is just 1. Now, whenever you see such an expression where you have functions that are orthogonal to each other, you can use the orthogonality in the sense that multiply both sides by sine theta, PL prime of cosine theta, and integrate over theta from 0 to pi. Now, why do we do that? Because if you look at the left-hand side becomes L equals 0 to infinity of the integral of sine theta, PL prime cosine theta, PL of cosine theta, from 0 to pi. This should be equal to V0, integral of d theta, sine theta, PL prime of cosine theta, P0 of cosine theta. Now I know the properties of these Legendre polynomials, that I already know the value of this integral, and that integral is 2 over 2L plus 1 if L and L prime are equal, and it is 0 otherwise. I wanted to get this expression, that is why I'm multiplying with sine theta and also PL prime of cosine theta. On the other side, well, this is a similar looking expression, so its value is 2 over 2L prime plus 1, but this is only if L prime is equal to 0, and it is 0 otherwise. Now let's look at the left-hand side. I'm summing over all possible values of L, but this Kronecker delta tells me that only the term L is equal to L prime contributes. So instead of the sum, I get a single term, AL prime, A to the power L prime, of 2 over 2L plus 1. This is equal to 2 over 2, no, this is L prime, 2L prime plus 1, Kronecker delta L prime is 0. Well, basically these I can cancel. So these coefficients are 1 if L prime is equal to 0, and 0 if L prime is different from 0. So you see the right-hand side is 0 if L prime is non-zero. So I can cancel this A to the power L prime. So L prime, this coefficient is just 0. If L prime is equal to 0, then the right-hand side is 1, the left-hand side is AL prime, this is 1, because it is 0. Yes, I have a V0 over here. So this was my general expression for the potential inside. This term is the general expression for the potential. No, this is the general expression for the potential inside. Now we had shown that this AL coefficients, only the L equal to 0 term is non-zero, all the other ones are 0. Well, the L equal to 0 terms, P0 is just a constant 1. R to the 0 is just 1. So we only have A0. Now this is what we expect because we started with two spheres. They are both equipotential surfaces, so we can basically replace them by conductors. We can think of them as conducting spheres or shells. So within a conductor, the electric field is 0, so the potential has to be 0. So that is what we actually find. So the potential inside is just constant, it's equal to V0. Now let's look at region 2. Now in this region, the potential expression will have this form. Because the problematic parts could have been R is equal to 0. And in the previous, in region 1, we had to say that B coefficients had to be 0. But in region 2, we don't have R is equal to 0 point. The other possible problematic point is R is equal to infinity. In that case, if the potential is finite at R is equal to infinity, this AL should be 0. But that R is equal to infinity is not in our region 2. So in both of these coefficients, in general, can be non-zero. Nothing we can do about that. But we have now the boundary conditions. We have two boundary conditions. One is V0 should be equal to, from L is equal to 0 to infinity, AL, A to the power L plus BL over A to the power L plus 1, PL of cosine theta. Again, we do the same trick. Just multiply both sides by PL prime sine theta and integrate over theta from 0 to pi. Well, basically, we have exactly the same expression over here in the above part. The only difference is that instead of that coefficient, we have a different coefficient. So I will just borrow from our previous results. AL plus BL over A, this is equal to V0 if L is equal to 0, 0 if L is different than 0. Well, let me write these coefficients. Because if you look at the previous expression over here, I have AL, A to the power L. Now I also have to add the B term. This is equal to this one over there. Because we are looking at the R is equal to 0. R is equal to A. We are given that when R is equal to A, the potential is V0. Now we will look at V1. Now at R is equal to B, this is our other boundary. We know that V1 is equal to L from 0 to infinity, AL B to the power L plus BL over B to the power L plus 1 times PL of cosine theta. And just do the same thing, and we would end up having AL B to the power L plus BL divided by small b to the power L plus 1. This is equal to V1 if L is equal to 0, and 0 if L is different than 0. Now we have two sets of unknowns and we have two sets of equations. Let's look at the L is non-equal to 0 case. But that tells me that a to the power L plus BL over a to the power L plus 1, this is equal to 0. And AL b to the power L plus BL divided by small b to the power L plus 1, this is also equal to 0. Well, this tells me that AL is equal to BL, this is equal to 0. They are both 0. Now we need to look at the L is equal to 0 case. Well, when L is equal to 0, A0 plus B0 over A, this is equal to V0, and A0 plus B0 over B, this is equal to V1. Now we need to solve these equations. Well, the easiest I can see, just subtract them. That will give you B0 times 1 over A minus 1 over B. This is equal to V0 minus V1. So B0 is equal to AB over B minus A times V0 minus V1. This is our B0. Now we can determine A0. A0 should be, let's say from the first equation, V0 minus B0 over A. So this is equal to V0 minus B over B minus A times V0 minus V1. And this is equal to minus A over B minus A, V0, plus B over B minus A, V1. And this is our A0. Now let's write down our potential. You see, this was the general term, the general form of the potential. I only have the A0 and B0 term. A0 term is just a constant because L is equal to 0. This is just R to the 0, 0. P0 is already 1. And this term is B0 over R. So the potential is A0 plus B0 over R. So let's see, this is equal to minus A over B minus A V0 plus B over B minus A V1 plus AB over B minus A V0 minus V1 times 1 over R. This is our potential. Well, it's likely that we had made a mistake somewhere, so let's check our result. You see, it trivially satisfies the Laplace equation. The potential is a constant plus the 1 over R. So if it satisfies the boundary condition, then it is the correct answer. So let's say let's look at the value at R is equal to A. This is equal to minus A over B minus A V0 plus B over B minus A times V1. When R is equal to A, the A's cancel. B over B minus A times V0 minus V1. Well, I have plus B over B minus A V1. Here I have minus B over B minus A V1. They will cancel. So I'm left with B over B minus A over B minus A, but that is B minus A over B minus A, V0. This is equal to V0. So it does satisfy the boundary condition. Well, let's see. You see, we have these two equations, these two ones. So what I did first was I subtracted this one from this one, eliminated A0, so I ended up having this equation for B0. Once I know B0, I just looked at this one. This equation tells me that A0 is equal to V0 minus this one. So A0 is equal to V0 minus B0 over A. This is equal to V0 minus, well, this is my B0. If I divide by A, this just disappears. V0 minus B over B minus A, V0 minus V1. I have V0 here, I have 1 minus B over B minus A. That is minus A over B minus A, V0. And then I'm left with V1, and that is minus minus makes plus plus B over B minus A, V1. Now, if I made a mistake somewhere that I couldn't see now, we will see it now. Let's just check the boundary condition at R is equal to B. V at R is equal to B. This is equal to the same coefficient. But this time we have this 1 over B. This is equal to, well, let's see, the B's cancel. I have minus A over B minus A V0. Here plus A over B minus A V0. So they would cancel each other. This term is cancelled by this one. I have B over B minus A V1 minus A over B minus A V1. So if I just combine them, I end up having B minus A over B minus A V1. This is equal to V1. So the solution I obtained, it was constructed to satisfy the boundary conditions. But of course, it's possible that we made some mistake. In our steps, we might have forgotten some minus sign, some other factors. So just to make sure, we checked our result that it satisfies the boundary conditions. And we had actually shown that it does satisfy the boundary conditions. So that is our solution.
Şimdi general solution'da zaten finding independence olduğunu söyledik. Aynı zamanda independence olduğunu da söyleyemez miyiz?
We can. I mean, in fact, that is what we are actually finding. So since it doesn't depend on theta, only the L equal to 0 term can contribute. We could have done that. So since the potential is independent of theta, any theta dependence on the right-hand side should disappear. But that tells me that all the Legendre polynomials depend on theta unless L is equal to 0. So in fact, that is what we are always finding. Only the L equal to 0 term can be non-zero. Well, I didn't want to decide to determine the possible values of L. I wanted the computation to tell me, or derivations to tell me. So this is my condition. This is what I have to satisfy. Let's go back in region 1. So I have to solve this equation. No, the one over there. That this sum is equal to some constant that I called V0. Now then I use the property that this integral of the Legendre polynomials is 0 if I don't have the same Legendre polynomial, and it has some constant value, some known value if they are the same Legendre polynomials. That's the property I wanted to use. So in the above expression, I multiplied both sides by this expression and integrated so that I will end up having this integral in my expression. Well, when I integrate this one, this is 0 if L and L prime are different, if they are different Legendre polynomials, and it is 2 over 2L plus 1 if they are the same Legendre polynomials. So that's the right-hand side. So the right-hand side just becomes this coefficient times a to the power L multiplied by this coefficient times this Kronecker delta. And this Kronecker delta just tells me that only the L is equal to L prime term survives in this infinite sum. I have infinitely many terms, but after this procedure, only the L is equal to L prime term is non-zero. All the other ones are 0. So I end up having the left-hand side just becomes a L prime, a to the power L prime times 2 over 2L prime plus 1. This is the right-hand side. Now, when I look at the left-hand side, I have a similar expression, but this time instead of PL, I have P0. And when I take that integral, only if L prime is equal to 0, the right-hand side is non-zero. Otherwise, it is 0. So this is the expression I obtained now. But the left-hand side is proportional to AL prime. The right-hand side is proportional to Kronecker delta L prime 0. And this is 0 if L prime is different than 0. So AL prime, I know that A, this radius is non-zero. So AL prime has to be 0 if L prime is not equal to 0. So that is how I decided. I didn't make any assumption. I didn't see it at first, but the calculation told me that only the L equal to 0 term is non-zero. But your friend has noticed another property of this system. He said that if you look at this expression over here, or let's say even look at this one, this relation, the left-hand side is independent of theta. So the right-hand side should also be independent of theta. But that means we have the theta dependencies over here. They should all disappear. So he said that without doing all those multiplication by the Legendre polynomial and sign and integration tricks, he said that this coefficient should be 0 if L is different than 0. Because if L is different than 0, we have a theta dependence over here. L is equal to 0, Legendre polynomial is just 1. It doesn't have any theta dependence. So he said that this has to be 0 if L is different than 0. And this coefficient has to be equal to V0 if L is equal to 0. Because only the term L is equal to 0 is non-zero in this sum. And the L is equal to 0 term is just, well, this one with L is equal to 0. Because P0 is 1. So it has to be equal to V0. And just by looking at our solution, we can even straight away write down what Q0 is, what is the charge of the inner sphere. One over 4 pi epsilon 0. Q0 has to be equal to this one. Because you see the position-dependent contribution in region 1 will be only due to the inner sphere. Because the outer shell will just give a constant potential in region 2. And that position dependence should be 1 over 4 pi epsilon 0 Q over R. So this is our Q0. Let's do region 3. Well, as your friend has realized, the potential should be independent of theta, so only the L equal to 0 term should survive. So we can use it straight from the beginning. This will be AL, A0, or let me give this a new constant, C0 plus D0 over R times P0. This is also 1. Now we have the conditions, V3. As R goes to infinity, we are still in region 3. The potential will become C0, but this should be 0. Because we are assuming that at infinity the potential is 0. That's our reference point. V3, when R is equal to B, which is D0 over B, this should be equal to V1. That is our boundary condition. So this tells me that D0 is equal to B times V1. So we are done. The potential in region 3 is just B over R times V1. Now we have determined the potential everywhere. This is the potential in region 3. Here we have the potential in region 2. And here we have the potential in region 1. Well, this will still be 1 over 4 pi epsilon 0, Q0 plus Q1. This is the total charge, because the potential outside the position dependence will be due to the total charge. This should be equal to B times V1. Well, let's go back. No, okay. No, sorry, this is B. We were looking at V1. V1 is at this point, at a distance B. So this is basically the expression we had. This is the same thing that we wrote before.
Hocam dördüncü soruda da bu dıştaki şişler için şey demiş. K cosine theta demiş. Surface charge density. O zaman o dielektrik bir madde.
So can you read the question?
Bunun aynısı sadece şey, V1 vermek için. Dıştaki surface charge density K cosine theta.
We have an inner sphere, and then outside we have a shell. Inner sphere is a conductor. Grounded or not, the potential of the conductor is V0. Outer shell we have a sigma, and sigma is equal to K cosine theta. And then we are required to find the potential where? Everywhere. In this region, in region 2. Hmm? Okay. Now, this time we don't have this theta independence. So because the charge distribution depends on theta, so we have in principle, we will have the contribution from all the possible L values. So let's start. Let's start with V2. Well, V1, we already know that it has to be equal to V0 everywhere. It's a conductor inside, the potential is constant, and it won't matter what we have outside. Inside the conductor, there's no electric field, so the potential is constant. Let's start with V2. V2 will have this form, AL r to the power L plus BL over r to the power L plus 1 times PL of cosine theta, L from 0 to infinity. Now we already know the potential at one boundary of region 2. V2, when r is equal to A, whatever the value of theta is, this should be equal to V0. This is already given. So this should be equal to sum over L, 0 to infinity, AL, the radius to the power L plus BL divided by A to the power L plus 1 times PL cosine theta. Well, this looks like the previous case. V0 is independent of theta. So in this sum, all the theta dependent terms should be 0. That is, if L is different than 0, this combination should be 0. So AL, a to the power L plus BL divided by a to the power L plus 1 should be equal to 0 if L is non-zero, and it should be equal to V0 if L is equal to 0. So if we impose this condition, we satisfy the boundary condition that R is equal to A. Now let's look at region 3. Well, this is still the most general in spherical coordinates. This is the most general solution. Even in region 3, it will look like this one with possibly different coefficients. But in region 3, we want the potential to be 0 at infinity. Well, these AL terms, they either diverge. If L is larger than 0, it diverges at infinity. If L is 0, it just becomes a constant. But we want the potential at infinity to be 0. So these terms should vanish in region 3. So in region 3, our solution looks like this one. CL over R to the power L plus 1 times PL of cosine theta. L from 0 to infinity. This is our region 3. So now we have our solutions in region 2 and region 3 satisfy the condition, the boundary conditions that R is equal to A, and they satisfy the boundary condition that R is equal to infinity. Now the thing left is we have to match these two potentials, because we have this boundary, the outer shell, the boundary on the outer shell, R is equal to B. The potential has to be continuous everywhere. Plus the potential, the electric field, since we have a surface charge density, the electric field should be discontinuous. And we know how much discontinuity we should have. So we should now impose those conditions. So at R is equal to B, V2 at R is equal to B, whatever the value of theta is, this should be equal to V3 at R is equal to B, whatever the value of theta is. This is the continuity of the potential. So this gives me sum over L, AL, B to the power L plus CL divided by B to the power L plus 1, PL of cosine theta. This should be equal to, from L 0 to infinity, this is B. CL divided by B to the power L plus 1, PL of cosine theta. Well, since PLs are what we call orthogonal functions, you can just think of as some orthogonal unit vectors. So if we have these two sides to be equal, the coefficients of the PLs on both sides should be equal. So that tells me that AL, B to the power L plus BL divided by B to the power L plus 1, this should be equal to CL divided by B to the power L plus 1. So let's see, here we have one equation, the first equation for our unknown coefficients. Remember, we have three sets of unknowns. We don't know AL, we don't know BL, we don't know CL. So we need three sets of equations relating these coefficients. So this is the first one. Now here we have the second one. Now we will obtain the third one by the discontinuity of the electric field. You see, we already know that the electric field, if we have a surface, electric field on the outside face of the surface minus the electric field on the inside face of the surface, this should always be equal to sigma over epsilon 0 times the normal vector. Normal vector is a unit vector perpendicular to the surface pointing from the inside to the outside. So in our case, I will just take n to be the radius vector. If you look at our problem, now we are looking at this boundary at R is equal to B. The normal vector is the radius vector. So I'm just putting it this way. So this is the outside, when I'm talking about the outside of the surface, I'm approaching the surface from region 3. When I'm talking about the inside of my surface, I'm approaching the surface from region 2. So that basically tells me that E outside is equal to minus the gradient of V3, and E inside, of course, that R is equal to B. This is equal to minus the gradient V2 at R is equal to A. Well, since the discontinuity is in the radial direction, only the radial electric field should be discontinuous. And that tells me that minus dV3 by dr, when R evaluated at R is equal to B, should be equal to minus dV2 by dr. R is equal to B should be equal to sigma over epsilon 0, and sigma is k times cosine theta, k times P1 of cosine theta over epsilon 0. Why P1? Because P1 of cosine theta is just cosine theta. Now you kind of already see the pattern. Here I will just take the derivatives, put the R is equal to B, and the left-hand side will be a sum of factored multiplying PL of cosine thetas. The right-hand side only contains P1. So on the left-hand side, the coefficient of PL of cosine theta should vanish if L is not equal to 1, and they should be equal to K over epsilon 0 for L is equal to 1. So that is what I will do. So that will give me my third set of equations relating these unknowns A, B, and C. So let's see. This is our V3. I need to take the derivative of, you see, I need to take, on the left-hand side, I need to take the derivative of this one with respect to R, and then set R is equal to B. If I do that, I will have sum over L is equal to 0 to infinity, CL times L plus 1 divided by R to the power L plus 2, now B to the L plus 2, PL of cosine theta. Well, this derivative with respect to R of this term is minus L plus 1 times 1 over R to the L plus 2, but in that definition I also have an additional minus sign. So this is the first term. Now the potential in region 2 is this one. Minus L from 0 to infinity, L B to the power L minus 1 plus, now here I have a minus sign, plus BL L plus 1 divided by B to the L plus 2 times PL of cosine theta. When I take the derivative with respect to R, I obtain L times R to the L minus 1. I have to put R is equal to B, and there is an additional minus sign in the above definition, above equation, because the electric field is minus the derivative of the potential. When I take the derivative of this one, I get a minus L plus 1 over B to the L plus 2. There is an additional minus, so the coefficient over here is positive. And this thing has to be equal to K over epsilon 0, P1 of cosine theta. Now, as I said before, on the right-hand side, I only have P1. So that should be true on the left-hand side also. So for L is equal to 1 term gives me C1 times 2 over B cubed minus minus A1 plus B1 2 over B cubed. This should be equal to K over epsilon 0. This is one equation I have. And then CL, L plus 1 minus B, no, let me write it in this way. CL minus BL sorry, here I have a, no. CL minus BL times L plus 1 over B to the L plus 2 plus AL times LB to the power L minus 1. This should be equal to 0 if L is not 1. And this is my third set of equations. I have 3 sets of unknowns, 3 sets of equations. Now I should be able to find them all. Let me combine my equations. So these are my equations. Now the easiest to solve will be if L is non-zero, is not equal to 0, and L is not equal to 1. L can be 2, 3, 4, etc. In that case, this combination is equal to 0. This is always satisfied. And that combination over there is also 0. So we have 3 sets of linear homogeneous equations for these 3 sets of unknowns, but the only solution is if all of them are 0. So if A and B and C, they are all 0, if L is not 0 and L is not 1, then I satisfy all 3 equations trivially. Now, they can have non-zero value only if L is equal to 0 or L is equal to 1. And each one of these we have to solve separately. So let's look at the L is equal to 0 case. Now, if L is equal to 0, from here, you see if L is equal to 0, the right-hand side is already 0. The second term is already 0 because it is proportional to L. So the first term has to be 0. But for the first term to be 0, C0 has to be equal to B0. This is from equation 3. But if C0 is equal to B0, look at equation 2. C0 is equal to B0 for L is equal to 0. So the second term on the left-hand side is equal to the right-hand side. So the first term has to be 0. So that is A0 is 0. Now let's look at the first one, the first equation. We are looking at L is equal to 0 case. Well, A0, we already had determined it is 0. So that tells me that B0 over A is equal to V0. Or B0 is equal to A times V0 from equation 1. So we already know that A, L, B, L, and C, L, they are 0 if L is 2, 3, 4, etc. Now we know what their values are. For L is equal to 0, also A0 it should be equal to 0. And B0 and C0, they are non-zero this time. They are equal to each other, and they are both equal to A times V0. Now let's look at the L equal to 1 terms. Well, let's see, L is equal to 1. So we have this equation. Let me simplify it slightly. This is C1 minus B1 times 2 over B cubed plus A1. This is equal to K over epsilon 0. If L is equal to 1, this combination is 0. Now we are looking at L is equal to 1 case, remember? So if L is equal to 1, A1 times A B1 over A squared, this should be equal to 0. This is another condition we have. And finally, we have this one. Again, of course, written for L is equal to 1. Or we can write it in a different form, C1 minus B1 times 1 over B squared is equal to A1 times B. Let me give them some names, 4, 5, and 6. So we have to solve these equations 4, 5, and 6. Equation 6 just tells me that C1 minus B1 should be equal to A1 times B cubed. Equation 4 then tells me that, okay, C1 minus B1 is just A1 times B cubed, so this is A1 times B cubed times 2 over B cubed plus A1 should be equal to K over epsilon 0. Or this tells me that A1 is equal to K over 3 epsilon 0. Now we know A1. But we also know that C1 minus B1, which was A1 times B cubed, this is equal to K over 3 epsilon 0 B cubed. Now we still have one more equation to satisfy this 5 from equation 5. I know that B1 should be equal to minus A1 times A cubed. So B1 is equal to minus K over 3 epsilon 0 times A cubed. So this is our B1. C1, this is equal to K over 3 epsilon 0 B cubed plus B1. You see I have that equation over here. This is the one I will be using. C1 is just this factor plus B1. We had already determined B1. This is K over 3 epsilon 0 B cubed minus A cubed. Now we had already known that all the coefficients are 0 for L is equal to 2, 3, 4. Now we know the coefficient C1, B1, and also A1 for L is equal to 1. And we already had already calculated what for L is equal to 0, A0, B0, and C0 are. So we know the solution. Let's write it down. The potential in region 2. Remember, this was equal to L from 0 to infinity, AL, R to the L plus BL over R to the power L plus 1 times PL of cosine theta. Well, L equal to 0. A0 is already 0. Yes, A0 is 0. B0 and C0, B0 is A times V0. A times V0 divided by R. This is the L equal to 0 term. In fact, this is nothing but the contribution to the potential from this inner conducting sphere. Plus, now we have the L is equal to 1 term. Well, A1 is just K over 3 epsilon 0. This is our A1 times R, plus B1 is minus K over 3 epsilon 0 A cubed divided by R squared P1 of cosine theta. So this is equal to A times V0 over R plus, let's just take out the K over 3 epsilon 0 R cosine theta term out, 1 minus A cubed over R cubed. So this is equal to A V0 over R plus K over 3 epsilon 0 times Z 1 minus A cubed over R cubed. Does this ring any bells? Do you remember this form? So we had already studied this problem of a conductor in a uniform electric field. Now, it's not really a surprise. You see, we have this potential, this charge distribution. The charge distribution, as your friend has pointed out, it just looks like the charge distribution of a uniformly polarized dielectric. And we had already seen that a uniformly polarized spherical dielectric creates a uniform electric field inside. So inside, the problem is we have this conducting sphere in a uniform electric field. So this is what we obtained. I didn't know it beforehand, so now we see this result. It's the derivation that told us what the potential should be. Now let's look at the potential outside. V3, remember it was L from 0 to infinity, CL over R to the power L plus 1 times PL of cosine theta. We already know that if L is larger than or equal to 2, all the coefficients CLs are 0. So this is C0 over R to the power C0 over R, P0 of cosine theta, plus C1 over R squared, P1 of cosine theta. This is equal to, well, C0 we had already calculated. You see, C0 is just A times V0. Again, it's just as if we have this point charge at the center. Plus C1, well, C1 was K over 3 epsilon 0. b squared minus a squared. Now b cubed minus a cubed. Times cosine theta over r squared. In fact, this is the dipole moment of the system. So we have this system with complicated charge distribution. Outside, for an outside observer, it just behaves like a point charge at the center plus a pure dipole. This 1 over r is always the monopole, and this is the dipole. The quadrupole, octupole, etc. moments of the system, they are all zero. Because this is not an approximation, this is the exact potential. And whatever the potential is outside the charge distribution, you can always write it as an infinite sum over the multipoles. But in this case, only the monopole and the dipole terms are non-zero in this infinite expansion. All the other ones are zero, turns out to be zero. So this is a system which doesn't have an octupole or a quadrupole moment. But the strategy that we are using, whatever the problem is, you first find the general solution in that coordinate system, and then use, if your region is divided into various parts with different properties by conductors, now we will be dealing with dielectrics, etc. For each one of those regions, you should write down the potential separately, and then if you know the boundaries, then you should impose those boundaries, boundary conditions. If you don't know the boundaries, but rather those are the boundaries that you kind of invented to separate, divide your region into various parts, you have to match the potentials in these boundaries. Either by you have to require that they should be continuous at the boundary, plus their derivative should be discontinuous if there is a surface charge. The trick, the strategy, the steps are always identical. It might take long. I mean, the derivations are not just two-line derivations, but the kind of the method is straightforward. Let's give a break, a 10-minute break, and after the break we can continue.